Okay, let's continue our discussion about time varying uniform plane wave. So here is an example. So in example 3.11, it provides an electrical field intensity description. So as you can see here, we first recognize the electrical field have both X and Z components. So the electrical field varies in both X direction and Y direction. AX and AY. And you can recognize the variable within the field distribution is in the form of omega t minus beta z. So, and the variable are the same for both the AX and AY components, which means they have the same time variant and wave propagation behavior. Okay, so we know that they are of the same frequency, and it can be recognized as omega. And the propagation direction, what is the propagation direction? According to the variable, it's in the form of minus beta z. So it's propagating in the positive z direction. Propagation is in the positive z direction. So if the variable is in the form of omega t minus beta x, then we know it's in the positive x direction. And if it is omega t plus beta y, then it's propagating toward the minus y direction. So it's a very simple rule to determine the propagation direction. And the next is to recognize some key parameter. So first we can recognize the omega and beta from the description of the variable. That is 3 pi times 10 to the 8 t minus beta z. So 3 pi times 10 to the 8 is its omega term. It's it's this number. And beta can be identified as pi. And we can also derive more intuitive parameters such as the frequency f, which is in the form of omega over 2 pi. So accordingly, we know the frequency is 1.5 times 10 to the 8, which can be also shown as 150 megahertz, right? And beta, according to the phase constant beta, the wavelength lambda can be found as beta over 2 pi. So it can be found as 0.5 or 1 over 2. Then a quick check for the, OK, 是吗？我到这，对哈 ，OK 好 ，Thanks for correcting me 。那 beta equals to 是吗？OK。All right. So that's because I haven't taken my daily dose of coffee. All right. So a quick check for the calculated number is you can find the phase velocity, VP, as the product of f times lambda. So that will combine to form as 3 times 10 to the 8th, which is correct. 你破我的梗了，我本来是要写的明天午餐算起来是错的，可以回去检查。OK， 好 ，right. All right. And in the example 3.11, we are asked to find the variable parameter associated with the wave. As you can see, we already defined a couple of them, and find the corresponding magnetic field expression for the H. And the frequency, as we have shown in the blackboard, they are 1.5 times 10 to the 8th. As for the frequency and wavelength is 2 meter, which is in the form of 2 pi over beta. And the velocity of phase velocity can be found as either the product of lambda and f or omega over beta, which are both 3 times 10 to the 8th, which is a rather familiar number we have for electromagnetic wave. Then we are asked to find out the magnetic field intensity expression, which can be done by taking the cross product of the propagation direction A, AZ, cross E. That will give you the expression for the magnetic field intensity. And note that because the electrical field intensity is greater than H by a factor of the intrinsic impedance, which is shown as eta sub 0. So you need to divide it, the cross product result with 377. So you can find out the result as this. And now that originally for the E component, that will be AX and AY. And the cross product result of AZ cross AX will produce the direction of AY direction, and AZ cross AY will give you minus AX direction. So the end result of the magnetic field intensity is a little bit different than the H field and the E field. So you should check up with your answer carefully. All right, and next is example 3.12, which is an example of the so-called antenna array, 天线阵列, 天线阵列. Array antenna is kind of a hot topic for electromagnetics in terms of application in the past few decades, because due to the advances of semiconductor and computation resource and the development of algorithm, it becomes less costly to produce or to make the array antenna, which involves not only the antenna design prospect, but also control and other. You need to be cooperated with other disciplines. But anyway, the main advantage of array antenna is that the radiation direction of the antenna can be manipulated, can be controlled electronically by which can be operated in a pretty timely fashion. One example is the ages. One example for the array antenna is ages. Ages is 神盾就军用的那个神盾雷达系统传统的那个军用雷达，它都要靠一个蝶形天线那边转，了不起就是1秒转一圈，所以它在监控周边的海域或周边的空域的时候，它 一次只能监控有限的数量。但是像神盾雷达、神盾舰上面的神盾雷达，其实它就是利用电子的方式，对使用一个阵列天线来去产生多个波束，或者同时产生的多个波束，或者快速切换波束，所以它可以理论上它可以同时监控上百个目标物了，所以这个是阵列天线的功效。那传统上都是阵列天线，因为贵其实成本高控制复杂，所以它的使用都在军用上面。但其实随着半导体技术计算机资源的进步，所以其实现在越来越多的商业应用都开始用阵列天线，包含像是你说的那个，其实像那个什么 Starlink。Starlink 的马斯克的 Starlink， 你去买它的设备也不过就几万块钱台币一套里头它所附的那个地面站的那个接收天线，其实也是阵列天线OK， 我认为它的成本其实不止几万块了不过现在应该还是在商业推广时期，所以卖的比较便宜一点 OK。Alright, so come back to the example 3.12. He provides some example to look at the principle of the array antenna operation. So let's consider two infinite plane parallel current sheet. So instead of just having one current sheet, now we have two. And the spacing, the distance between the two current sheet is a quarter wavelength, lambda over 4, which is also named as quarter wavelength. So what is the significance of a quarter wavelength? 1/4个波长它代表什么意义？ Well, a quarter wavelength suggests there is a 90-degree phase difference. So for one signal, one electromagnetic wave propagating at a distance of a quarter wavelength, it shall change its phase by 90 degrees. Similarly, if the propagation distance is half a wavelength, then the phase change is 180 degrees, and if the propagation distance is 1 wavelength, then the phase variation is 360 degrees. All right. So in this example, we place one current source, J as 1, at the position of Z equal to 0. And the other source, which is named as J as 2, is placed at a position of Z equals to lambda over 4, a quarter wavelength. And the signal, which are sinusoidal signal of the same frequency, as you can see here, they both have the omega parameter. So JS1 is minus JS sub 0, J sub S0 cosine omega t. And JS2 is cosine omega t minus pi over 2. So the variable are time with adjustment in its omega, in the omega. So as you can see here, if you compare the two functions, they are of the same frequency. They are of the same frequency, nevertheless, the two signal has a phase difference. One is lag of the other by pi over 2, which equals to what? Equal to 90 degrees. Pi equals to 180 degrees, 2 pi is 360 degrees, so minus pi over 2 is a lag in phase by 90 degrees. So we have two infinite source plane, current plane, and they are of the same frequency, but the phase of the two are different by 90 degrees. And also the spacing between the two current sheets is a quarter wavelength. All right. And so in the previous page, we have seen the description for the current J1, JS1 and JS2. Now we can elaborate a little bit about the electromagnetic wave generated by the two current sheets. All right, so the electromagnetic wave produced by JS1 goes to both sides. The component goes to the positive direction, is in the form of eta sub 0 over 2 times cosine omega t minus beta z, right? In x direction. And this description is valid for z greater than 0, in the region of z greater than 0. On the other hand, for the region of z smaller than 0, the electrical field is eta sub 0 over 2 times Js sub 0, J sub S0 over 2 times cosine omega t plus beta z. Now that in this half, in the left half, the propagation direction is in the minus z direction. All right. So that's the electrical field produced at the position by the current at the position at z equal to 0. We can do the same thing for the other current, J sub S2, which can be written as minus J sub 0 cosine omega t minus pi over lambda. Or you can transform the difference toward pi over lambda as the sine function. So let's just apply the textbook. We see that it also have two components. One is propagating to the positive z direction, the other toward the minus z direction. So for the positive z direction part is 2 eta sub 0 j sub s0 over 2 times sine omega t minus beta z for z greater than lambda over 4. All right? And the other component is, I missed something. Okay. All right. Because the position of JS2 is at z equal to lambda over 4. So the other component is for z smaller than lambda over 4, right? So if you compare the two parts, you identify that the very last term in the sinusoidal function is z minus lambda over 4, which can be turned into, if you times beta, which is 2 pi over lambda, it can be turned into pi over 2, which equals to 90 degrees. And again, this can be rewritten as which is the same as the positive Z component in this region, for Z greater than 0 for the JS1 currents. So we can identify that the two are exactly the same for regions for greater than lambda over 4. And if you look at the other part, and you do the same transformation, first substitute lambda over 4 as pi over 2. And again, you made a change in the function from sine to cosine, and because this one is lagged by pi over 2, it turns out to be a negative, there's a negative sign in the front. So, for this part, in this region, it's this becomes minus eta sub 0 j sub s0 over 2 cosine omega t plus beta z. For this region. And now we have three regions. One is for region at z greater than lambda over 4. The other is z smaller than 0. And the region in between. So for region of z greater than lambda over 4, you have addition of two functions of similar expression. So the total field, total electrical field, due to the contribution of JS1 and JS2 is eta sub 0 JS0 cosine omega t minus beta z. Okay? For z greater than lambda over 4. So, well, it's what kind of field is this? What is the significance of this function? It's a propagating wave. It's a propagating wave, propagating toward the positive z direction. Which is I would refer to it as a traveling wave. 行进波，也就是说，在 z 大于 lambda over 4的这个区域，来自于 JS1 跟 JS0 的电场，它们刚好是同样的形式。那为什么会刚好呢？原因是它们的间距是1/4个波长，相当于90度的相位差，而它们的讯号本身也刚好差了90度，所以左边的那个所以右边的那个讯号跑到左边的时候，刚好弥补那个相位差，所以在 z 大于4/4 lambda 的那个区域以右边，也就是 z 大于这个部分的话，这两个电场是刚好同相位的。同相位的话，那就是1+1等于2所以它的总体的电场强度是这个结果。On the other hand, if you look at the region of z smaller than 0, then you will have this function plus this function. The contribution of JS1 and JS2 shall be added again. Nevertheless, due to the excitation, phase difference in the excitation and due to the displacement, the distance between the two current sheet, the contribution from JS2 becomes minus eta sub 0 j sub s0 over 2 cosine omega t plus beta z. They are the same function of opposite sign. 所以这两个在 z 小于0的这一个区域 ，JS1 跟 JS2， 它们的电场的变化关系式是一样的，但是差一个负号，差180度。所以呢， E1 加 E2 等于0 for z smaller than 0. So for the region z smaller than 0, you will observe no field because the phase difference in excitation and because of the difference in the propagation distance. All right, so in the region of z smaller than 0, you have no field, 0, no field. Okay, how about the region in between? You will have these things plus this thing. Plus what? Plus what? Plus what? Plus blah, blah, blah. Plus this thing. You will have the addition of the two functions. So let's take a look at the result. So in the middle, you have eta sub 0 j is 0 over 2 cosine, you have cosine omega t minus beta z plus cosine omega t plus beta z minus cosine omega t plus beta z. So what is the result of this thing? 这叫什么 ？cosine 的 alpha 减 beta 加上 cosine 的 alpha 加 beta 所以用简单的三角函数整理一下。注意一个是 omega t 减 beta z， 一个是 omega t 加 beta z， 在中间那一块区域，所以它加出来的结果变成这个。这个你自己要验证一下。So in the region that is z between quarter wavelengths and 0, the addition of the field becomes eta sub 0 j 0 sine omega t times sine beta z. So, do you have field in this region? Yes. Does the field vary with time? Yes, because you have a sine omega t dependence. Does the field vary with position? Yes, because you have the dependence of sine beta z. So there are fields appearing in the middle between the two current sheets. However, can you refer to it as a traveling wave, as a propagating wave? Well, the answer is no. Why? Because the variance function in the middle region is the time dependence and the spatial dependence are independent. Unlike the one over here, which shows you that the spatial and time dependence are coupled together. In the middle, they are separated as two functions. So you simply observe the product of two functions. So the time variation and the spatial variation are not coupled to each other. So they cannot represent as a traveling wave. It's not going. But it's, as you can see, you still observed field variation in this region. So this thing is referred to as the standing wave, 驻波所以从这个是一个蛮重要的结果，请大家要试着把这个物理现象做一个理解也就是说，当然这边加起来，因为刚好是反向的，所以它没有讯号，没有讯号也代表什么？那个地方没有能量。因为电磁波那个电场跟磁场其实是能量的代表，所以空间中有电场有磁场的代表有能量出现在这个空间当中。而在 z 大于1/4波长1/4兰达的这个区间呢，你看到的是一个行进波。为什么说它是行进波？因为它的 variable 同时包含了对时间与对位置的描述，所以它的能量是在往正 z 方向跑的。这两个电流源所产生的电磁场，它们是一起往前跑，它会往前一直传播下去。 但在中间的话呢，它就比较特殊了，刚好一左一右，一个往左边跑，一个往右边跑，所以它在那边来回震荡。有没有能量？有，但是它是一个储存在空间当中的能量，那这一个储存能量的形式叫做驻波，就跟你在弹吉他一样，当你拨弦的时候，你事实上是把机械能转换成弦上面的动能，这个动能，那个弦会慢慢的，那个振动会慢慢的越来越减小，为什么？因为那个弦振动的动能会慢慢转换成声波的 acoustic wave 的能量 ，OK？ 那你去拨那个吉他弦的时候，你会根据弦的长短发出哆来咪的声音嘛，对不对？那个哆来咪的 pitch 是怎么决定的？根据你的弦长度嘛，根据你的波长的长度嘛。那个弦的装置让你去产生特定频率的一个振动，但吉他的那一个弦在振动的时候，我们是看到了能量的出现。但是那个能量不太能跑，除非它再转换成 acoustic wave 的形式，不然它传不出去。那当然你说，我听得到那个哆来咪的声音，那什么？你已经看到它的，你已经感受到它的 acoustic wave 的能量嘛，但是那个弦的声音那个吉他弦振动的声音就会持续一段时间之后就会消散因为能量已经被跑掉了。OK， 所以这一个物理现象请你要去理解它所以这边我们看到的是两个电流面的电流的所转换出来的电场讯号，在空间中，在各个在这3个区域里有建设性的相加，因为它同相位；破坏性的相消，因为它刚好差180度，以及它因为传播方向的相反，它形成了一个驻波能量卡在那里，但是并没有没办法传出去。你有能量，但是它传不出去So the total field is 0 in the region of z smaller than 0 due to the phase opposition of the individual field, and there is no radiation toward the left-hand side of the array. For the region of z greater than quarter wavelengths, the total field is twice that of the field of a single sheet, because individual field from the two sheets are added up in phase. So they are the power is greater. And in the middle region is the so-called standing wave. So here is an illustration of the total field. Okay, so我这张图画的不太对了这边z 小于0的部分是对的因为你这边看到它两个是 out of phase， 所以它加起来蓝线是等于0。中间的那个区域其实应该是这一个实线不是蓝线，蓝线是错的实线是这两个讯号加在一起的结果所以它有可能是0，但有可能会变大那右边呢则是两个讯号，实线呢则是代表细实线跟虚线的这个相加结果因为它们同相位，所以它们的那个大小会变成是2倍。所以对于这样的一个阵列来讲，我们可以看到它的有效的能量辐射方向，它的电磁波辐射方向是往右边的那因为这一个辐射方向是在阵列排列的侧边，所以我们称之为它叫 end-fire direction. Right? Here's an example which I perform using the numerical EM tool. So it's a simulation tool that we have for the design of antenna. So in this example, I have made 2 antennas, the so-called dipole antenna, and the spacing is quarter wavelengths as specified in this example. And here is the simulation region. So you see that we have 2 dipole antenna placed in the middle of the simulation space. Then we are interested in about to observe the phase addition and cancellation in this region. So here is the simulation result of the 2 antenna. One is antenna, the phase of antenna 2 is lag behind antenna 1 by 90 degrees. So the total field, as you can see from this animation, is propagating toward the left, toward the minus y direction in this example. And there's very little field to the right, appears to the right. And so of course you can see there's some field in between. But it's in the form of the standing wave. Maybe you can see, check out another example here. Now the phase difference is altered by antenna 2 lead by antenna 1 by 90 degrees. So the propagation direction is changed to propagating toward the y, toward the positive y direction, toward the right-hand side of the plot. And how about this case? In this case, the phase of the two are the same. And as you can see here, it's propagation on both sides. Here's a simple example to demonstrate the concept of array antenna by altering the phase and the position of element antenna or the individual antenna sources. You can manipulate the propagating direction. Of course, in reality, the phase array are more complicated, all right? So we shall conclude our discussion about 3.5 here.